From this point on, for every new class of compounds, we'll talk about their physical properties before we move on to the properties that are much more interesting to us, and that is chemical properties. Alkanes are nonpolar molecules because all of their bonds are relatively nonpolar carbon-hydrogen, carbon-carbon bonds, and as such they're insoluble in water. They're soluble in organic solvents, nonpolar organic solvents. And because they're insoluble in water, they're actually good lubricants for metals because they prevent moisture and aqueous water from reaching the metal and corroding it. And so that's why mineral oils or other alkane derivatives are used as lubricants. Their density is slightly lower than that of water, so it's about 0.7 grams per centimeter cube. Relative to water's 0.1, 1.0 is lower, so they float on water. Okay? In terms of their boiling points, they, as we discussed previously when we talked about London's forces, vary with the number of carbon atoms. So the more carbons we have, the higher the boiling point. So for methane, the boiling point is minus 164 degrees centigrade. However, for decane, C10H22, the boiling point is 174 degrees centigrade, so much higher. If we're going to plot this chart, where as our y-axis we have the boiling point and as our x-axis we have the number of carbons, then we'll see that there's this curve where it slowly levels off as we get to higher carbon numbers. And these will be the individual alkanes. Okay. This curve applies to straight chain alkanes. And analogously, branched chain alkanes also have this curve that levels off, but it's slightly offset, slightly lower. And the reason for that is they're more spherical, so they hold each other relatively weaker, and because their interaction surface is lower, so that's why their boiling point are lower. In terms of their melting points, a similar relationship is observed between the size and the number of carbons. However, one thing that is different is that while this curve overall has the same shape, it zigzags. And these, for example, would be alkanes with an odd number of carbons, while these, a little bit higher ones, will be the ones with an even number of carbons. And the reason for that is that even number of carbons means that the compounds can better pack in a crystal. So then the melting point is higher. So better crystal packing is responsible for this zigzagging of melting points. Finally, and this is somewhat counterintuitive, branching raises the melting point because arguably the gaps in the crystal structure can be filled with these branches and the crystal packing unit is better. So again, this is an effect which is a little difficult to understand perhaps, but if you look at these couple of isomers of hexane, their boiling points, as we discussed already, decrease with branching because the molecules become more and more spherical in their interaction surface. But the melting points, increase with branching.